Good time of day. My name is Dan Fruman and I would like to present to you our work on compositional reasoning about non-interference for fine-grained concurrent programs. This is joint work with Robert Krebers and Lars Birkedal. Before we go forward, let me briefly explain what kind of problem are we trying to tackle here. The question that we are trying to answer is this: how to reason compositionally about non-interference of fine-grained concurrent programs in a foundational manner. There is a lot of jargon in this sentence, so let me unpack it a bit. By non-interference, we mean a specific notion of security that guarantees that a program does not leak secret information, as we will detail later. We are considering non-interference specifically for fine-grained concurrent programs. That is, concurrent programs that use non-blocking atomic instructions, such as compare and set and fetch and add, instead of less granular synchronization primitives like locks. We want to reason about non-interference of such programs in a compositional way. For example, if we have a library and a client using this library, what do we need to know about both of these components separately in order to conclude that their composition is secure? Can we prove non-interference, possibly under some conditions, for the library and for the client separately, and they compose the proofs together? Finally, we want to take a foundational approach to non-interference proofs, with all the notions formulated against some agreed upon operational semantics of a programming language formalized in the proof assistant. So, let us talk a little bit about what we mean by non-interference, since it is a notion that we heavily rely on. Non-interference formalizes the notion of security for a computer program. We start with some program E that operates on some sensitive data. Let us suppose that the data is stored in the variable secret. We say that the program E satisfies non-interference if varying the secret data in the program does not lead to observably different behavior. So an attacker who observes the behavior of E from the outside couldn't tell the difference between E operating on the secret data being integer 0 or being integer 1. Intuitively, this means that the secret data is not leaked to an attacker. For those who are familiar with non-interference, the specific notion of observational equivalence that we use in this work is strong low by simulation of Sabelfeld and Sons. Here are some examples of programs that do not satisfy non-interference. As we can see, the first program leaks the secret information by directly printing it onto the screen. This is an example of a direct information leak. The second program, on the other hand, exhibits an indirect information leak. Depending on the value of the secret data, the program can output different numbers to the screen. The third program leaks information through the termination behavior. On the face value, such termination leaks might not provide much information to the attacker, but their effects can be aggravated, especially in presence of concurrency. Now, determining whether a program satisfies non-interference can be quite complex, especially in the presence of programming language features like concurrency. Let me try to illustrate this with the following running example written in an OCaml style language. At the beginning, we create a new record R. It contains two mutable fields, the field data, which stores an integer, and the field isClassified, which stores a boolean. Initially, the data field contains some secret value, and the idea is that the isClassified bit tells us whether the information stored in the data field is actually secret or not. With this record R initialized, we run the following two threads in parallel. The rightmost thread does the following. It first overrides the secret information in the data field of R with some junk, and then it sets the isClassified bit to false. The thread on the left acts as follows. It spins in an infinite loop, and in each iteration it checks whether the isClassified bit is set to false. If that is the case, the thread prints the value of r.data onto the screen. This program is secure. It does satisfy non-interference. To see this as formally, note the following two facts. First, if the isClassified bit is set to false, then the information stored in r.data cannot be secret. Secondly, once the secret information is overwritten, the r.data field does not get assigned secret information ever again. Both of those facts are quite important. Note that, for example, if we switch around the two lines in the rightmost thread, the program violates the first condition and becomes insecure. This is because in the right thread, the assignments can be the rightmost threads can be interrupted between the two assignments, leaving the record R in an incoherent state. The left thread can then observe this incoherent state, reading the value of is classified, and drawing incorrect conclusions from that. Well, what I've shown here is but an informal argument. How do we make it precise and establish no interference formally? Or better, can we establish no interference of this program compositionally? That is, can we identify what do we need to know and establish of the subprograms, the left and the right threads, to derive no interference of the program as a whole? This is what we mean by compositional no interference. Alright, let us take a step back and talk about how we can enforce no interference. One of the most popular ways of establishing compositional no interference, at least on the level of programming languages, is by using a type system. Typically, you would have a type system which types are annotated with sensitivity labels. H for high sensitivity for secret data, and L for low sensitivity for public data. In the typing judgment on the screen, we see a program E that returns a low sensitivity integer, and it operates on the variable X, also containing a low sensitivity integer, and a variable Y, which contains potentially secret data, as determined by the sensitivity label H on its type. Type systems are popular because they are fundamentally compositional in their nature and can be extended with various programming language features, although not always in the most obvious or straightforward way. On the other hand, type systems are too weak when it comes to programs where non-interference depends on functional correctness properties and some protocols on data structures, as was in the previous example. This in particular means that a conventional type system would not be strong to verify no-interference of the previous example with the record R and two threads. That is, the typing judgment of this program is not going to be derivable. In order to account for such programs, we use a technique called semantic typing. The idea behind it is as follows. The job of a type system is to delineate between programs with good behavior and bad behavior. However, a typing system is described by a set of inference rules, usually in such a way that the type checking is decidable. So, a priori, type checking cannot be used to check behavioral properties in all the possible cases. Now, under semantic typing, instead of using inference rule, we take a typing judgment and we generate a predicate which describes what kind of behavior the typing is actually supposed to delineate. Then, instead of checking that a program E satisfies some typing judgment, we instead verify that the generated predicate holds for the program E. This allows us to leave the world of typing derivation and use the whole power of mathematical logic. For this approach to work, we need to ensure that all the typable programs do indeed satisfy the generated predicate. This approach is great for reasoning about combinations of typed and untyped code. If our program consists of both, then we can simply type check the typed part of the program and separately verify the untyped part of the program. In fact, this approach has been previously successfully applied in the context of the type system for the Rust programming language in the Rust Belt project. There, the type system guarantees safety of programs, and generated contracts were called safety contracts. In this work, we instead consider security contracts, which guarantee not just safety, but also no interference. In the modern approach, such as the one used in the work on Rust Belt, the safety contracts are written in Hoare logic. That is, a typing judgment gets translated to a specific Hoare triple. This works quite well, as Hoare logic is tailored towards proving safety. In our work, we introduce another program logic, which we call CLOC, and which is aimed at proving non-interference. The key idea behind CLOC is to internalize the notion of a strong law by simulation inside the logic. So instead of Hoare triples, we have propositions of this shape, which we call double weakest precondition, or DWP for short. Intuitively, this proposition says that E1 and E2 are in some sort of bisimulation, and if they terminate with some results, then these results satisfy the predicate phi. One way to think about it is that E1 and E2 are essentially the same program, but with varied secret input. And the double weakest precondition ensures that they produce the same publicly observable behavior. Um, as such, we have the following soundness theorem. Suppose that we have a program E with a secret variable named secret. We then take this program E and produce two other programs by replacing the secret variable E with values h1 and h2 respectively, where h1 and h2 are arbitrary values. We then ask that the two resulting programs are related by DWP. In the post condition, we further ask that the resulting values v1 from the first program and the v2 from the second program are in fact equal. If that holds, if we can derive this proposition in C-log, then we know that the program E satisfies non-interference. Another important ingredient in C-log is a mechanism for defining and enforcing protocols on programs and data structures. As we mentioned, C-log is a program logic. Specifically, it's a concurrent separation logic. Concurrent separation logic is an extension of OR logic which is geared towards reasoning about concurrent and stateful programs. We built C-log on top of the concurrent separation logic framework IRIS. And as such, we inherit a lot of useful features like invariance and custom ghost state, which are crucial for reasoning about concurrent programs with custom protocols on data structures. I will not go into details on this, but I would like to illustrate this on our example. So recall this program from before with the record R and the two threads operating on this record. We are going to formalize this protocol on the record R as a transition system containing three states corresponding to how the record R evolves. In a way, this transition system tells us the life story of the record R. Initially, R is in the classified state, meaning that the isClassified bit is set to true and the data field contains sensitive information. Let us first look at the rightmost thread. The first thing we do in the right thread is override the data field. This moves this transition system into the intermediate state, meaning that the isClassified bit is still set to true, but the R data field still doesn't contain any sensitive information anymore. Then the program sets the isClassified bit to false. This moves the transition system into the final state, declassified. So the rightmost thread evolves the reference R in accordance with the protocol. Now let us see how the leftmost thread can rely on this protocol in order to show no interference. First, when we check the isClassified bit and it is set to false, that is, if we're actually going to take the then branch, then we know that the system has to be in the declassified state, because that is the only state where the flag can be set to false. Then, when we reach the output command, we know that the system still has to remain in the declassified state, because this state doesn't have any transitions from it. So that means that the record R could not have evolved into a different state in between those two operations. So whatever is stored in the R.data field is non-sensitive, and we can output it to the screen. Now, I'm not going to show the details of how this protocol is actually encoded in the logic, but I just wanted to show on this slide that it is indeed possible to do so, and there is a semi-systematic way of encoding protocols and transition systems like this. Please see the paper for more details. So, in conclusion, we have presented C-log, a novel relational separation logic for proving non-interference of fine-grained concurrent programs. To our knowledge, it is the first program logic to tackle non-interference in the context of fine-grained concurrency. It is fully formalized in the Coq proof assistant, including all the examples and utilizing the powerful IRIS separation logic framework. We have shown how to construct a model of an information flow control type system using the methodology of semantic typing. Please see the paper for more examples and a more thorough explanation. Thank you very much for your attention. And don't forget to hit that like button and subscribe to the channel.